Hey everyone, welcome back. In C++, understanding object lifetime is absolutely critical for efficient and correct memory management. Whether you are writing high-performance code or trying to avoid bugs like dangling pointers or memory leaks, knowing when objects are created and destroyed is essential. Let's start with the basics. There are four primary types of object lifetimes in C++: automatic, static, dynamic, and temporary. Automatic lifetime. This is the most common and happens when you declare a variable inside a function. The object is created when the function is entered and destroyed when the function exists. These are also known as stack-allocated objects. Here is an example. Automatic objects are fast and convenient, but you have to be careful not to return references to them from a function. That leads to undefined behavior. Static lifetime. Objects with static lifetime exist from the start of the program until the end. They are initialized once and destroyed only when the program exits. There are a few places you can get static lifetime: global variables, static variables inside functions, and static class members. The key feature of static objects is that they retain their value across function calls, but because they live so long, they can also introduce bugs if overused. They also introduce issues in multi-threaded code if not properly synchronized. Dynamic lifetime. Dynamic objects are those you create with new, and you're responsible for deleting them with delete. Every new must be paired with a delete. If you forget, that's a memory leak. If you delete twice, that's undefined behavior. Modern C++ encourages using smart pointers to manage dynamic memory safely. Smart pointers like std unique pointer and std shared pointer reduce the risk of leaks and make your code cleaner. Temporary objects. Temporaries are unnamed objects created as intermediate results. Their lifetime is short, usually the full expression. In the shown case, the temporary result of the concatenation is used to initialize the return value. Temporaries are often invisible but important. They are destroyed at the end of the full expression unless extended. C++ has rules to extend the lifetime of temporaries, especially with const references. But if you bind a non-const reference to a temporary, it won't compile. This helps prevent dangling references. Why object lifetime matters. Misunderstanding object lifetime leads to serious bugs. Here is a classic example: returning a reference to a local variable. This compiles, but the result is undefined behavior. You might read garbage or crash. Another issue is memory leaks. This happens when you allocate memory but you forget to free it. Leaks add up over time and can crash long-running programs. Smart pointers solve this by releasing memory automatically. Dangling pointers are also a lifetime issue. You might have a pointer to an object that's already destroyed. Accessing a dangling pointer is undefined behavior. Let's now briefly talk about RAII. Resource acquisition is initialization. This C++ idiom ties resource lifetimes to object lifetimes. Here is a simple class using RAII. When a file handle object goes out of scope, the file is automatically closed. This is clean and safe. This is why lifetime management is so powerful. A few more lifetime subtleties. You can return objects by value without worrying. C++ 11 and beyond optimize this using return value optimization, or move semantics. You are not copying the string here unless the optimizer can't apply return value optimization. This makes returning objects by value not only safe but often efficient. In contrast, references and pointers need more caution. Let's talk about temporaries again, especially with function arguments. This is valid and safe. The temporary lives long enough to be used, but take care when storing references beyond the call. This looks okay, but is actually dangerous. Now let's see how lifetimes apply to class members. Here, my class doesn't manage the memory. If the pointer passed to the constructor is deleted elsewhere, my class has a dangling pointer. This is where ownership semantics come in. If my class owns the pointer, it should use a smart pointer like std_unique pointer. Now the object owns the memory and will clean it up safely. Another subtlety is default arguments. Here the default temporary guest is valid because it's bound to a const reference. Again, temporary lifetime is extended. Finally, remember that static objects are initialized once. This can cause issues with initialization order if you are accessing globals across different translation units. This is the static initialization order fiasco. To fix that, use function local statics. This ensures instance is initialized on first use, and C++11 guarantees thread-safe initialization. So to wrap up, use automatic storage when possible. It's simple and fast. Use static storage cautiously. It lives forever and can cause bugs. Use dynamic storage only when necessary, and prefer smart pointers. Understand temporaries, when they are stored, when their lifetime is extended, and avoid dangling references. By mastering object lifetime, you avoid memory leaks, crashes, and undefined behavior. And you write modern, safe, idiomatic C++. That's it for this video on object lifetime in C++. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one.